Today we are going to be talking about geometric sequences. By the end of this video, you should be able to describe a geometric pattern, and you should be able to write a rule to describe both arithmetic and geometric patterns. First, in a geometric sequence, each term is found by multiplying a constant, r, called the common ratio, to the previous term. When we looked at arithmetic sequences previously, we were adding a constant to get to the next term. Here we are multiplying by a constant to get to the next term in the sequence. So here we are told that this sequence is geometric. We have 4, 12, 36. So we need to look and see what we are multiplying by each time. Here we multiply by 3. Here we are multiplying by 3. So we are going to continue that pattern. We want to find the next 3 terms, so we continue multiplying by 3 to get 108, 324, and 972. Next, we want to write an expression for the nth term. So first, I'm going to write a recursive rule. Remember that for a recursive function, we have to say what the first term is, which is 4, and then write a rule in terms of what we are doing to that first term. We already said that we are multiplying by 3, so this means we are going to do 3 times the previous term. And this would be our recursive definition for this sequence. If we want to write an explicit definition for this sequence, we know that we are multiplying by 3 each time. So geometric sequences are very similar to exponential functions. The number that you are multiplying by, or your common ratio, is going to be the base of the exponential. There are a couple ways that we could write this rule. If we want to have 3 to the n power, then we have to make sure that we pick a value so that our first term is 4. If we plug in 1 for n, 3 to the first power is 3. So to make our first term be 4, we would have to multiply by 4/3. The more common way of writing a geometric sequence is you have your first term times your common ratio to the n minus 1 power. All 3 of these rules, both the recursive and the 2 different explicit rules, do accurately describe our sequence. But the third one is probably the most common. Next, we want to write the first 4 terms for this sequence. We know that a sub n is equal to -1/3 to the nth power. So if we plug in 1 for n, we get -1/3. If we plug in 2 for n, we have +1/9. If we plug in 3 for n, we have -1/27. And if we plug in 4 for n, we get +1/81. So those are the first 4 terms. Here, to find the nth term of any geometric sequence, you want to use the formula a sub n equals a sub 1 times r to the n minus 1 power. Remember that a sub 1 is the first term and r is the common ratio. So this is the format that I used when I wrote this third function for our first example. So we want to find the 15th term if we know that the first term is 20 and the common ratio is 1.05. So if we use this formula, our n is going to be 15. So we have that a sub 15, or the 15th term, is equal to 20 times 1.05 to the 15 minus 1. And then you just plug that in the calculator, and you get that the 15th term is approximately 39.599. Next, we are told that we have a geometric sequence. We know that the 4th term is 125, and the 10th term is 125 over 64. So I'm going to write out some blanks. We know that the 4th term is 125. And we know that the 10th term is 125 over 64. So the first thing we need to find is what r is. We know that we multiply by r to find the next term in the sequence. So here we are multiplying by r. Here we are multiplying by r. Each time we multiply by r. So if we start with 125, we multiply r times r times r times r times r times r. So we're going to multiply by r 6 times, which is the same as r to the 6th power, and that will give us 125 over 64. And then we just solve this equation. If we divide both sides by 125, we get r to the 6th is equal to 1 over 64. Then we take the 6th root of both sides and get that r is equal to 1/2. But since we are taking an even root, so square root, 4th root, 6th root, 8th root, etc., we could have positive or negative 1/2. We do not know for sure. Now, we are asked to find the 13th term. So we do not need to write out the rule for this sequence, but you could if you wanted to. You just need to figure out what the first term is, and then you can write the rule for the nth term. We need to find the 11th, 12th, 13th term. So we can just continue to multiply by positive or negative 1/2. If we are multiplying by positive 1/2, we would end up with the 13th term being 125 over 512, because we would get 125 over 128, 125 over 256, and then 125 over 512. If we are multiplying by negative 1/2, this 11th term could be positive or negative. The 12th term would be positive, and then the 13th term could be positive or negative. So we do not know for sure, but the 13th term in this sequence is either positive or negative 125 over 512. Now, let's take a look at the sum of a finite geometric series. We have our general formula, which is that the sum is the first term times 1 minus r to the n over 1 minus r. So we want to find the sum for this given sigma notation. Since we are going from k equals 1 to 12, we know that we are adding up 12 terms. We need to know our first term. So if we take 1 and plug it in for k, we have 4 times 0.3, which gives us 1.2. And this number that is the base of the exponential is going to be r. Then we can just plug this into the formula. We have that the sum of the first 12 terms is equal to 1.2 times 1 minus 0.3 to the 12th power over 1 minus 0.3. If you plug this in the calculator, you get that the sum of the first 12 terms is approximately 1.714. Obviously, the other way to do this is to write out the first 12 terms and add them up, but this is a more efficient way. The last thing we want to look at is the sum of an infinite geometric series. In some circumstances, you can add up an infinite sum. If you look at the formula, this says the infinite sum is equal to the first term over 1 minus r. That is only possible when the absolute value of r is less than 1. So let's think about that for a second. If we have something like 1, 1/2, 1/4, 1/8, 1/16, etc., our function is decreasing. If we graphed these points, we would end up with an exponential decay function. It has a horizontal asymptote, and the sequence is approaching 0. In this circumstance, this is called a convergent sequence, and you can find the infinite sum. But if we had something like 1, 2, 4, 8, 16, etc., the numbers are getting bigger. If you look at the end behavior of this exponential function, the numbers will continue getting bigger. They approach positive infinity as you keep progressing through the sequence. This is called a divergent sequence. And you cannot find the sum of an infinite sequence that diverges. So let's look at our last example here. We want to find the sum from 1 to infinity of 4 times 0.6 to the n minus 1. Similarly to the last problem, if we plug in 1 for n, we find that the first term is 4. R is always going to be the base of our exponential. Since r, or the absolute value of r, is less than 1, then this sequence will converge, so we can find this sum. So if we use our formula, this infinite sum is equal to the first term over 1 minus r. If you plug that into the calculator, you get 10. So adding up an infinite number of numbers in this sequence, you end up with 10.